Hello, everyone. So today I'm talking about LNet observability, and packet tracing. So the first big question, what is Lustre doing? Why is it doing it? I think most people have probably asked themselves this question at least once. I know I have many times. I think a lot of it comes back to the Lustre protocol. If you look at something like NFS, it's formally specified, right? You can look at the source code of like the Linux NFS implementation. You can look at the spec. You have a pretty good feel for what a system call might do on the network. Lustre, you're kind of forced just to read the source code. It's a little bit better than maybe some proprietary storage systems where you can't even do that, but it's not as good as it could be. So a big question is, how do we actually improve this situation? I guess that's the title of this slide. Request tracing is my approach. So there's a few existing solutions that people use to varying degrees. There's static trace points. If you ever look through the source code and see like a C debug or a C error message, those are essentially like Lustre native static trace points. They emit things to, the Lustre debug log. You can scrape all of that manually. You can do like request tracing. I think it's like D_net or something that you can enable. Very performance intensive. It will slow down your machine if you enable that. And there's also like native Linux like trace points. Lustre doesn't really use those right now, but it's similar kind of concept, right? You're taking a text log, you emit it to a buffer, and then you have to read it. There's also stuff like BPF trace, other kind of like out-of-the-box BPF solutions. Very good, very powerful, but Lustre doesn't ship any of these tools by default, so you have to basically write a script yourself. So you have to go look at what the Lustre data structures look like, try to come up with something that would poke at those directly, and yeah, not great. And there's like TCP dump, right? You can like do a TCP dump of something, throw it in Wireshark, take a look at what the RPCs are doing. If you're using like a loopback interface, right, you have like your co-located client server, using InfiniBand, EFA, any of the HPC or HPE interconnects, you're kind of hosed. I think maybe some tools exist for some of those other network types, but I've never used them. So what's the solution? At least what's my idea of a solution, is doing native packet capture in LNet. So the way this at a high level would work is you create a TCP dump-like tool that can work natively with LNet using eBPF. So it's something that you could use out of the box, right? Prepackaged in like an RPM with Lustre. You don't have to know anything about how Lustre works. You can just run a few simple commands and see what the RPCs look like. So I'll give it a little bit of background about how some of these things work, just so if you're not super familiar. eBPF. For people that are not familiar, it's an extended Berkeley packet filter. It's basically like a lightweight virtual machine. So if you are familiar with like Java or Python, they take the high-level code, compile it down to a bytecode, and run it on a little virtual machine. eBPF kind of works the same way, except that it runs in the kernel, right? And you can read kernel data structures. So this is the from the Illustrated Children's Guide to eBPF. It's the best diagram I found anywhere for explaining how some of this works, but you basically have the user space program injects a little program into the kernel that gets run every time events happen in kernel space. So diagram there, and there's one that is a little bit more in-depth. You have a C source, that's your eBPF program. It's kind of like a special dialect of C in certain ways, more of a pain to write. That gets compiled down to the bytecode that I mentioned before, and then you load that through a system call to be run, runs through a verifier to make sure it's safe, it won't crash your system. And then it just gets run on a set number of events that you define ahead of time, right? So you call a kernel function, it runs your eBPF program. So that's one half of it, right? That's how we're going to capture packets. Now, the second half of it is where are we actually capturing them from? You have to capture that at the LNet level, right? So if you look at Lustre architecture, you have Lustre, like the application, on top of its own networking layer, LNet. LNet is there to basically provide you network agnostic message transport. There's a few key structures that exist in LNet that we want to poke at. There's the LNet message and the LNet MD. The LNet message is kind of like an accounting structure to say like, hey, I have this message. It needs to go to this place. Here's how I'm going to track it through its life cycle. The LNet MD is MD for memory descriptor. It's where the actual bulk of the packet lives. So you register a region of memory, you populate it with your packet information, you attach it to a message, and then you later on detach it and then free that packet. I have a little life cycle diagram here. It's kind of, could be a little bit prettier, but you can kind of see that flow that I talked about. You allocate a message, you attach it to a memory descriptor, you do some wire transfer, you detach it, and then you free both of them. The reason I bring this up is because if you go back a few slides, these little events, with a B next to it, these are the events that we have to start poking at to capture packets from LNet. You can't capture the packet before it's allocated, right? You can't capture it after it's freed, so you have to be very careful for where you're attaching probes to the different functions in the life cycle. So it's kind of alluding to this, the architecture of the tool that I'm describing. It's like you have the kernel provides a few very small interfaces that allow you to copy data from LNet structures. The eBPF program will basically use those interfaces, attach at a few key points in the message lifecycle, populate a ring buffer, and then the user space component, which is like the largest, heaviest weight part, will read that ring buffer and then parse it and give you some kind of useful output. I have something like a little UML diagram that kind of describes that in a different way. So you see there's a few like LNet load bytes, event load bytes. That's a very thin set of kernel interfaces we have to implement. There's a number of like LNet NI receive, send, so on, event handlers that we're going to be probing at runtime, and then use those special functions to scrape the message contents, throw it to the perf buffer, and then it goes into user space where you consume it, essentially. And you can kind of see, you have the kernel eBPF userland. It kind of rhymes with the earlier architectures that I was pointing out here, right? User space injects this eBPF program that creates this perf buffer. Then you read the results and parse them. So I'll skip ahead to this slide. This is what the tool output actually looks like, right? So you run a tool with a, essentially like a format string. It will scrape every single packet in real time, and then it will print out the individual fields that you get from that packet. This is like the current POC that exists. I even have a live demo on my laptop that I can show people if they are interested afterwards. But you can see the fields from left to right. You have like a counter of the number of packets that are being scraped. You have the XID, which is also the match bits, if you're more familiar with LNet. You have whether you're sending or receive the packet, whether it's an LNet get, put, reply, or whatever. You have the portal, so stuff like LDLM, cancel, request, reply, so on. OSD.io, OSC reply. You have the job ID, so you see like systemd, timesyn, or kworker, and then the actual opcode of the RPC. And you just collect this all in real time. Right now it's only a print output, but it's envisioned that you can also do maybe a pcap file, so you can open it in Wireshark or save it to some kind of persistent binary log, maybe on like an ongoing basis. And I kind of talk about some of these things in the preceding slide. I think the very basics of it, the kernel interface, the BPF interface, and the simple printing tool should be ready in a 218 timeframe. The tool exists and it's working, it just needs to be polished up a little bit more. And you got to be a little bit careful with the message life cycles to make sure you're not doing any invalid accesses. Some of the other stuff, metrics, binary logs, sequence charts, that kind of stuff, would be coming later. The design of it is kind of like a pluggable architecture. I don't have the plugin part totally implemented right now, but it's more of a function pointer, so right? So in theory, you could do something like take a packet capture, save it to a binary log, and then later on you can generate, a view like this, or like a histogram or a stats file, something along those lines. And then packet filtering. Right now, it's just grabbing everything, but with a little bit more BPF magic, you should be able to say, grab only a subset of packets that match particular patterns, right, and only populate the perf buffer with that subset. So it can performantly say, only get me LDLM and queues that are going to this particular MDS, right, and it'll only copy those guys over. That's something I'm hoping also to get in the first initial batch, so it's mostly just mutating the existing code a little bit. There's also another set of big feature that I'm trying to get in the initial landing. Essentially like RPC sanity checks. Some of this is needed for just testing the tool in the first place, but it could be used more broadly for answering some kind of harder to answer questions. So a good example is if you're doing like an ls-l, right, and you're curious whether or not stat ahead is being as efficient as it could be. You can look at proc files, sys files, things of that sort, or you could have some kind of filter and assert statement that says like, oh, this ls-l triggered this exact number of RPCs of, MDS requester, OS, OSD glimpse, so on and so forth. And I have a few other example questions of that might be interesting, like if you do a sync to the server, are you actually flushing the amount of stuff that you think should be flushed, right? Are you actually sending it over to the server? Or if you have a program that you've written that is touching the same set of files over and over again, how often are you dropping and reacquiring those locks, right? Is there some kind of locking scheme that you could do that's better? Or if you're doing, last one's kind of generic, but are you being too chatty with your application, right? Is there an issue in Lustre? Is there an issue in how your application is doing I/O patterns? That kind of stuff. There's a few other stuff that I didn't list on this slide that's maybe like next steps. If you go back to this slide, right, the LNet load bytes, you might think about the reverse storing bytes. A lot of the eBPF hooks in the kernel also have a store bytes where you can essentially overwrite a field in your RPC and go a step further and even like recompute the checksums of that RPC as you're overwriting fields. That's something that I want to look at some point. Beyond 218, very likely. There's also routing. So UDSP right now is you define a fixed set of rules. It's not very programmatic. But with some of these hooks, you should be able to, read a packet, make some kind of routing decision, and then pass that back to LNet, which could be very powerful. You could do something like, direct metadata messages over one route and direct bulk I/O over another route. things like that. I'm not sure, always open for suggestions if anyone has any ideas of ways that could be useful. But the general long-term goal is to find ways to make eBPF more readily accessible to people that want to use Lustre and LNet. This is kind of a starting point, just grabbing the packets, interpreting them, putting them in a form that people can make use of more readily. But I imagine this expanding over time, right, as new use cases come up, right? If you look at some of the eBPF documentation for the Linux kernel, there's a very rich set of operations that you can do that LNet is not doing right now. And we really could make a lot more strong leverage of it. Yeah, that's pretty much everything I had. It's not a super long talk, right? I have a demo of this tool working on my laptop over there. You can take a look. Happy to walk through it more. Happy for more suggestions. But until then, stay tuned for 2.18, right? I'll have the initial bit of this tool. But yeah, that's it.
Thank you very much, Tim. That's looks like a great tool that we'll have in our arsenal. Are there any questions for Tim?
So I have a couple questions. One is, how is this any better than a Wireshark with an appropriate plugin?
It's not necessarily better right off the bat, right? So if you are using sockets, right, and you can use TCP dump and use Wireshark, you can get similar set of features. There's a few things you miss out on. You can't snoop on loop back traffic between co-located client and server. That's common in a lot more cloud deployments.
I mean, you definitely can. You just need to disable the hand in LNet that does not route it through the kernel.
Yeah, but then you lose some of the performance, I guess, of doing loopback. The long-term vision for a tool like this is efficient enough and lightweight enough that you could run it in theory on a production host, right? Just continuously doing monitoring, which is not something I think you would want to do for TCP dump.
I mean, I guess. It's just with your preface, when you started with the Lustre login is not appropriate for any of this. It almost sounded like you would provide observability into the actual flow of state inside LNet. And that's what I was actually hoping for. All that, if you just capture the packets and replace them, you're not going to hit all the same races and stuff. But, there's a whole bunch of debug prints that goes into the debug buffer. And this is why people typically enable debugging in LNet, and it just overwhelms everything. So you have nothing to actually cover that aspect of it, right?
There's, it wouldn't be like a comprehensive replacement. The key point there was people really can't enable the C debug for RPCs without huge performance impact. eBPF is a lot more efficient, so you could, in theory, get more information from a live system.
Right, but this is not that part, right? This is just capturing packets. It has no captures for C debug or anything.
It does capture messages on different parts of the life cycle. So you can probe three things, right? Just like the LNet NI send and receive. You can probe the events that are coming off of the LNet event handlers. I think I call out some of them, like portal RPC master callback, for example. And you can probe the life cycle of the MD. So you can get most of the important parts of the RPC lifecycle, I think.
Okay, I mean, but not the individual kind of messages coming out of the LNet or other part, right? Or I guess that's possible. It could be its own separate event when we want to emit something like, hey, we are in a strange state here, right? Or no?
I don't think it would be anything like that.
Okay, thanks.
Yeah.
Couple questions as well. Have you measured any performance impact of this? I'm sure you have a prototype.
I did some very limited testing. It was, I want to say, 10% impact, somewhere around there. It was not really comprehensive testing. I've looked at some other network tracing tools using eBPF to see what their performance impact was, and they were able to keep it in kind of like single-digit percentage impact. That's kind of the goal. I don't know how feasible that is, right? If you had something like a giant DGX box and you're doing like a huge number of 4K IOs, that would probably be the worst case scenario. I'd want to get some kind of performance impact on that once it was merged and more ready.
Okay. Second one is more of a comment, not a question. I see a huge attack surface potentially here, security implications.
Not any more than just normal eBPF. There is a little bit of care that you have to take with the LNet like load bytes and future store bytes to make sure that you actually validate inputs correctly. But to actually load the eBPF programs into the kernel, you have to be sudo or super user, right? Run sudo.
All right, thank you.
This looks really cool, thank you. One thing I was wondering about is you kind of mentioned that the Lustre protocol is not exactly documented and sort of the implementation is the specification in a way. I was wondering if as part of this there could be an effort to kind of document that protocol more and sort of specify it in a way. I mean, looking at that example output, it's like some of the packet types are pretty self-explanatory, but then some of them I have no idea what they mean. So I'm wondering if there's any effort to kind of more formally document that.
Yeah, there was a historic effort to document the protocol that exists. If you look at the git.whamcloud, look around, you can find their old protocol doc. I read through it. It has a decent amount of information. It would be useful to revive some of that. This was actually, I envision it as kind of the first step towards at least being able to make a second client implementation to do like just poke at a Lustre server, or maybe do a simple like get put object type thing. That was more so like for development purposes or maybe like RPC level fuzzing. But I would like to see this situation improve at least a little bit. If you look at something like S3, for example, S3 is also not formally specified anywhere. It's entirely implementation dependent, but on the flip side, there's other third-party implementations that people understand pretty well and are pretty understood. So I think Lustre could probably get to a state that's kind of similar to S3, where it's like maybe you don't have a full formal doc, right? But people understand it enough that they can at least explain their workloads in terms of RPCs or things like that.
Yeah. So how do you make sure your tool, if you build a tool in this kernel, how do you make sure your tool work for the other kernels?
Yeah. So a little bit of a complex topic. There's a concept of BPF co-re, so C-O-R-E. It's compile once, run everywhere. It's you extract the type information from the kernel. There's some transformations that go on that allow your BPF code to be, in theory, kernel agnostic. I've tooled around with it. The current build process uses that like co-re idea. I still run into issues with the verifier every once in a while, or reject something that was previously working. Got to play around with it a little bit more to get a little bit more happy with it. I think for most people that use Lustre, they won't have to worry about it too much because you're already consuming the kernel modules, right, that are built for a specific kernel. So if you have a eBPF thing that is only tested to work on the particular kernel, that's not the end of the world. But yeah, like at least the wider eBPF community has, you know, solutions in this direction, so I think we can adopt most of those, just kind of rote.
Yeah, so the issue is that, BTF is actually not available everywhere. Like, as long as you have BTF available, yes, you have a happy path, right? But if not, it's gonna be difficult.
Yeah, there's actually some patches floating around to prepackaging the BPF type information with Lustre. The tricky part is it's how the kernel is packaged and whether the kernel will export the BTF virtually. So if you're in the most happy path, if you're running the kernel that you're trying to compile your BPF for, there's a sys entry, like a sysfs entry, that you can poke at to get the BTF information directly and compile your eBPF stuff. Otherwise, you have to hope that the distro that you're, whatever you're running on your platform actually has the BTF package installed, right? Or BTF actually configured on the kernel. Not great solutions, but it's something that we're going to have to solve one way or another if we want to use prepackaged BPF tools with Lustre.
Does this work on the LNet router as well?
Yeah, it should. I haven't tested it, but it's nothing Lustre specific. Any LNet service could make use of this. So if you run LNet self-test, you should be able to snoop those packets. I know there's Cray DVS. I don't know how well adopted that is these days, but it should work for that as well. You'd have to add some enums probably in the parsing code, but I intend to write a few simple LNet services to do some tests for this. So services that are just send a GET request, send a PUT request. Very simple measured services, just so I can do some validation that it actually correctly picks those messages up.
Any more questions?
Kind of just, something to exercise LNet like that deliberately would be fantastic when troubleshooting buggy firewalls and clients and stuff.
Yeah, I thought about, this is not something I've worked on or plan to work on in the near term, but some kind of simple user space interface for LNet that allows you to, form a packet and send a packet from a user space program would be kind of useful, and that's probably, I might look at doing it for this testing. If it takes too much effort, I might just do a kernel module and then defer the fancier thing to a later time.
Okay, thanks again to Tim. Give him another round of applause.
Thanks.